This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter and Tumblr. Just search for SpaceTime with Stuart Gary.
Astronomers have detected a puzzling ice cloud that's apparently formed out of thin air on the Saturnian moon Titan. A report in the journal Geophysical Research Letters claims the cloud detected in Titan's stratosphere is composed of a compound of carbon and nitrogen known as dicyanoacetylene, C4N2, an ingredient in the chemical cocktail that colours the giant moon's hazy brownish-orange atmosphere. Decades ago, infrared observations by NASA's Voyager 1 spacecraft detected a similar ice cloud on Titan. What's puzzled scientists ever since those original Voyager observations was that they detected less than 1% of the dicyanoacetylene gas needed for these clouds to condense. And now, the recent observations from NASA's Cassini mission have yielded a similar result. Using Cassini's composite infrared spectrometer, which can identify the spectral fingerprints of individual chemicals in Titan's thick atmospheric brew, researchers found a large, high-altitude cloud made of the same frozen chemical. Yet, just as Voyager found, when it comes to the vapour form of this chemical, the infrared spectrometer reported that Titan's stratosphere is literally as dry as a desert. The study's lead author, Kerry Anderson from NASA's Goddard Space Flight Center in Greenbelt, Maryland, says the appearance of this ice cloud goes against everything science knows about the way clouds form on Titan. Now, whether it's Titan or the Earth, the typical process for forming clouds involves condensation. On Earth, we're familiar with a hydrological cycle, which includes the evaporation and condensation of water to form clouds. The same kind of cycle takes place in Titan's troposphere, the weather-forming layer of Titan's atmosphere, but instead of water, Titan has methane and ethane. A different condensation process takes place in the stratosphere, the region above the troposphere, at Titan's north and south winter poles. In this case, layers of cloud condense as the global circulation pattern forces warm gases downwards at the poles. The gases then condense as they sink through cooler and cooler layers of the polar stratosphere. Either way, a cloud forms when the air temperature and pressure are favourable for the vapour to condense into ice. The vapour and ice reach a balance point, an equilibrium that's determined by the air pressure and temperature. Because of this equilibrium, scientists can calculate the amount of vapour where ice is present. For clouds that condense, this equilibrium is mandatory, sort of like the law of gravity. But the numbers don't compute for the clouds made of dicyanoacetylene. Put simply, you need at least 100 times more vapour to form an ice cloud where the cloud tops were observed by Cassini. One explanation suggested early on was that the vapour might well have been present after all, but Voyager's instruments simply weren't sensitive enough in the critical wavelength range needed to detect it. However, when Cassini also failed to detect sufficient vapour, Anderson and colleagues proposed an altogether different explanation. Instead of the cloud forming by condensation, they think the C4N2 ice is forming because of reactions taking place on other kinds of ice particles. The authors are calling this solid-state chemistry. That's because the reactions involve the ice or solid form of the chemical. The first step in this proposed process involves the formation of ice particles made from the related chemical cyanoacetylene HC3N. As these tiny bits of ice move downward through Titan's stratosphere, they get coated by hydrogen cyanide or HCN. At this stage, the ice particle has a core and a shell composed of two different chemicals. Now, occasionally, a photon of ultraviolet light will tunnel through the frozen shell and trigger a series of chemical reactions in the ice. Now, these reactions could begin either in the core or in the shell. Both pathways can yield dicyanoacetylene ice and hydrogen as products. The authors got the idea for solid-state chemistry from the formation of clouds involved in ozone depletion high above Earth's poles. Although Earth's stratosphere has scant moisture, wispy nacreous clouds, also known as polar stratospheric clouds, will form under the right conditions. In these clouds, chlorine-bearing chemicals that have entered the atmosphere as pollution stick to crystals of water ice, resulting in chemical reactions that release ozone-destroying chlorine molecules. So it looks like Anderson and colleagues may well have found examples of similar solid-state chemical processes on both Titan and Earth. Of course, on Titan, the reactions occur inside the ice particles sequestered from the atmosphere. In that case, dicyanoacetylene ice wouldn't make direct contact with the atmosphere, which would explain why the ice and the vapour forms aren't in the expected equilibrium. While the compositions of the polar stratospheres on Titan and Earth couldn't be more different, it's still amazing to see how well the underlying physics of both atmospheres has led to analogous cloud chemistry.